Welcome back. In this section, we'll be talking about some properties of logarithmic functions. At the very beginning of the course, we talked about exponential properties, so how we could simplify things like a to the power of x multiplied by a to the power of y. So we have properties for things like this for exponential functions. We'd like to now have similar sorts of properties laid out for logarithmic functions. And so here we're going to talk about some of these basic properties of logs, as well as ways in which we can manipulate logarithms. Because eventually our ultimate goal will be to solve some equations that will involve logarithms or exponential functions. And to do that, we'll need to be able to manipulate these logarithms. So I'll start with some properties, some things that we know. The first one that we know is this. Again, we're thinking about the base being any positive a that is not 1. And we have this fact that log base a of itself is always equal to 1. And the reason we know that is, of course, a to the power of 1 is equal to a. So if you were to take that exponential expression and rewrite it as a log, it would be log base a of a is equal to 1. You also know this because of the graph. If you're thinking about the graph of log base a of x, you know it goes through the point a1. So you know that when x is a, that y is 1. So not a surprise, log base a of a equals 1. And you have similar sorts of reasoning for the second point here. You could say log base a of 1 is always 0 because you know the equivalent thing that you could say about exponential functions, that a to the 0 is equal to 1. Or you could think of it because you happen to know that every logarithmic function happens to pass through the point 1, 0. So again, you could think of this as being, you know that when x is 1 on a logarithmic graph that y must be 0 because it passes through that point 1, 0. Or you could think of it in terms of, you know log base a of 1 is 0 since a to the 0 is 1. These next two properties are actually properties of function inverses, just written in a little bit of a different way. Remember that for an inverse function, f composed with f inverse should get us just x, and f inverse composed with f should also give us just x. And since the logarithm and the exponential function with base a, since those are inverses of each other, then log base a of a to the power of x, putting an exponential function inside a logarithm, composing one function with another, that they should cancel each other out and leave you just with x. And same thing is also true for a to the power of log base a of x, putting a logarithm inside of an exponential function, composing a logarithm with an exponential function. That's putting a function's inverse inside of the function. That should give us just x as the result. So first two properties we could think of just again because of the fact that a to the power of x is the inverse of log base a of x. We could also think of it in terms of those are just points that we happen to know on the graphs of both functions. The other two properties are really properties again because logs and exponential functions are inverses of each other. And we've got some further properties, and these are properties that are, for the first few, similar to the sorts of properties that we had for exponential functions, but with a little bit of a twist. So with an exponential function, we knew that if you multiplied two exponential expressions, you would add the exponents. Here, this is a little bit of a different thing, where if you are adding two logarithms, you will multiply the arguments for those logarithms. You'd multiply the inputs together. Similarly, we had that if you had a to a power divided by a to another power, that you would subtract the exponents. The equivalent expression that we have for logarithms would be that if you were subtracting two logarithms, that's log of the first number divided by the second number. A couple of things just to mention about both of these first two properties, that for both of them they have to be the same kind of log, so they both need to have the same base. So if somebody says log base 3 of 2 plus log base 4 of 5, can I combine these? The answer is no, because they are not the same logarithm. They're two logs with different bases. But log base 2 of 3 and log base 2 of 7, that would be log base 2 of 3 times 7. And the same thing is true for the subtraction version of it as well. That would also have to require both of them having the same base. The next one that we have is this. This is sort of equivalent to the thing that we had said about what happens when you have an exponential expression raised to a power, and for that we were multiplying the exponents together. This is sort of a similar thing here where we have a logarithm multiplied by a number, and that number turns out to be now raised as a power on that inside of that log. So for example, if you had something like 3 times log base 2 of 5, that would be the same thing as log base 2 of 5 to the power of 3, or log base 2 of 125. And of course, these also work in the opposite direction. So for example, if you had log base 2 of 60, 60 is 6 times 10, so I could rewrite that as log base 2 of 6 plus log base 2 of 10. Or if I had, for example, log base 2 of 27, I know that 27 is 3 cubed, so that's the same thing as saying 3 times log base 2 of 3. So just like our properties for exponents where we could use them in either way, same sort of thing is true for these exponential properties. Sometimes I might take two logs and add them and combine them together to make one logarithm, or I might take one logarithm and split it into two, depending on what I need to do. The last property that we have here is if you have two logs with the same base, so they're both log base a, and if they are both equal to each other, log base a of m and log base a of n, why is it true then that we know that the inputs must be equal? And that's the question that I have here. How do I know that this last statement is true, that the inputs must be equal to each other? The fact that I said the word input is kind of the little hint here. If you're thinking about this, log base a of m, whatever you get, that would be the output of your logarithm. And log base a of n, whatever number you get, that would be the output of your logarithm. So really what we're saying here is if the logarithm has the same outputs, then they must have the same inputs, which is a fancy way of expressing that log base a is 1 to 1. Remember that for a 1 to 1 function, that if you have the same y values, then that means you must be talking about the same x values. So if you're thinking about a graph that is 1 to 1, there's my little logarithm that I'm drawing there. If you're thinking about a point and it happens to have a y value of, let's say, 5, and I think of a point that also has a y value of 5, we must be thinking of the same point because our graph only has one point where the y value would be 5. So if you have the same outputs, you must have the same inputs, and that's because log base a of x is 1 to 1. That's similar to a property that we have for exponential functions. If you know that a to the power of x is a to the power of y, If those are equal, then x and y have to be equal, and that's for the same reason. If the outputs for our exponential functions are equal, then the inputs must be equal as well, and that's because exponential functions are one-to-one. So we'll do some calculating here, and this is evaluating without needing to use our calculator. So I say here evaluate. I just want to know what the value is of natural log of e squared plus natural log of 1. And I know the first thing that I can do is take that 2 out front. Natural log of e squared should be 2 times natural log of e. And I know that for log base e, that e to the power of, that those are inverses of each other. When I say natural log of e, well, I'm really saying log base e of e. And remember, we had one of those properties that said log base a of a would always be equal to 1. So log base e of e, that is 1. And again, the reason you know that is because on the graph of natural log of anything, natural log of x, that it passes through the point 1e. That when x is 1, the y value is e. So natural log of e, I got those points backwards, sorry. I was writing but not thinking. E1 rather. If you have e as your input for your natural log, 1 should be the output for your natural log. For natural log of 1, that is 0. Again, we had the property on the previous slide that log base a of 1 is always 0. So log base e of 1 certainly should be 0 as well. Now, you can think of it from that perspective, or again, you can think of it from the perspective of the graph. For the graph of natural log, it passes through the point 1, 0. So when x is 1, y is 0. So for natural log of 1, the output should be 0. And then we just need to finish this off. 2 times 1 plus 0, that is 2. The properties that we have of these natural logs, this is one of the strength, or of any logs rather, this is one of the strengths of it, is that it allows us to come up with exact values in some cases where the individual logs themselves are not nice exact numbers. So if you're thinking about these, all three of these expressions don't turn out to be nice numbers individually. This would be saying 8 to what power is 6? Not any nice number. 8 to what power is 4? Again, there's no nice number where that's the case. 8 to what power is 3? There's no nice whole numbers that make that happen. All three of these, if you were to evaluate them using your calculators, and we'll talk about how you would be able to do that, all three of these would turn out to have infinitely many decimal places. But if we use some properties of logs, then actually we can combine this into one single log that we'll be able to evaluate directly. So first off, two logs with the same base being added together would be multiplying their arguments, multiplying what's being put in as the input. So when I say log base 8 of 6 plus log base 8 of 4, that would be log base 8 of 6 times 4, which is 24. So that's my first step. Secondly, now I've got one log base 8 minus another log base 8, and I know that when I'm subtracting two logs with the same base, that it would be log of the first number divided by the second number. So that's log base 8 of 8. Oh, okay, well, we know what that is. Log base a of a is always equal to 1. Log base 8 of 8 is 1. And then there we go. Our final answer to this question is 1. All right, so just a couple of little things where we're going to apply those log properties. I'm going to do one example where I'm taking a log and splitting it up into simpler, smaller logs that are being added or subtracted from each other. And then I'll do the reverse where I've got a bunch of logs being added or subtracted, and I'll combine them all together to make a single logarithm. This is the sort of thing that we'll need to do sometimes when we're solving an equation. Sometimes we'll need to split logs up, sometimes we'll need to combine them together, so we need to have a little bit of practice doing that. So first off, I have here log base 2 of a numerator over a denominator, and so I know right away I can split this into one log minus another log, log base 2 of the numerator minus log base 2 of the denominator. Okay. All right. So next thing that we have here is in our first term, I have log base 2 of two things multiplied. So using my log properties, that would be log base 2 of that first thing, log base 2 of cube root of x. And then I would have plus log base 2 of x minus 1 to the power of 3. I do want to be a little bit clear about notation just before I go any further, especially the notation here about these powers. This is something where you might misread this if you're not careful. I know some people in the past have thought that this cube was applying to the entire logarithm, which is not the case. Here, the cube is only attached to the x minus 1, so only the x minus 1 is being cubed. If I wanted to have an entire logarithm being cubed, then I would need brackets around the logarithm with the cube outside. That would be a logarithm that's being cubed. However, for what I've got here, it's not that the logarithm is being cubed, it's that x minus 1 is being cubed. And similarly here, it's x plus 2 that's being raised to the power of 4, not that logarithm. So we've done part of our job, which is to write things as sums or differences of logarithms. The other part we have to do is it says to express all powers as factors of logarithms. So in other words, if you have powers, bring them down in front and write it as a constant multiplied by that log. So I'll work my way from right to left this time, just for fun. You have log base 2 of x plus 2 to the power of 4, and that 4 will come down in front. So we'll have minus 4 log base 2 of x plus 2. And same thing for the second term, the one in the middle, the 3 can come down in front. And for my first term, log base 2 of cube root of x, remember a cube root is really power of a third. So that third can come in front. So we have 1/3 log base 2 of x plus 3 log base 2 of x minus 1 minus 4 log base 2 of x plus 2. And now we do the reverse. We're going to combine everybody and write them as a single logarithm. So I'll basically do the opposite of what I did here. Here, the last thing that I did was bringing the powers down in front. And then the first thing that I did was splitting up my logs into sums and differences. So I'll do the reverse. The first thing that I'll do is I'll bring the numbers that are in front up as powers. Then I'll deal with the minuses and the pluses to combine all of my terms together. So the first thing that I'll do is I'll bring those numbers in front as powers. So I'll have log of 3 squared minus log of x plus 2 cubed plus my log of x minus 1 to the power of a half, which of course That's the same thing as square root of x minus 1, so I'll just write that as log of square root of x minus 1. There we go. And next thing that I'm going to do is to start simplifying. I have one log minus another, so that would be 1 log of the first thing, which is 3 squared, or 9, over the second thing, which is x plus 2 cubed. One thing to note here is that these are all logs where there's no base being written, so even though there's no base being written, there is still a base. These are really the common logs, all logs that are base 10. That's the reason why I'm able to combine them together. They are all logs with the same base. And then finally, I have one log plus another, and when you have two logs with the same base that are being added, you are just multiplying their insides. So 9 over x plus 2 cubed multiplied by that root gives me 9 times that root over x plus 2 cubed. And there we go. There's our single logarithm for the expression that I started with. All right, this is the formula that we'll sometimes need to use if I want to find the value of a logarithm, approximate value, and it's not a common log and it's not a natural log. This is also answering the question you might have had if you looked at your calculator and you saw that there was only 2 buttons for logarithms. You might have been wondering, well, what if you wanted to evaluate other logarithms? The reason why we don't need multiple buttons, and in fact, you could probably even get away with only one logarithm button. You could just use natural log for the rest of your life and no others and still be able to do all the same things, because you can change logarithms from one base, in this case base A, to 2 different logarithms, both with the same base, in this case base K. So if you have any log that you'd like to look at, you can choose whatever base you'd like and rewrite it as log base k, your chosen base, of the argument m, divided by log base k, your chosen base, of your original base a. So for example here, I'm looking for log base 4 of 72. And if I wanted to evaluate that, I could rewrite this as log base 10 of 72 divided by log base 10 of 4. Or I could rewrite it as natural log of 72 divided by natural log of 4. Or any other base that I felt like using. This would also be log base 3 of 72 divided by log base 3 of 4. Or any other number you feel like choosing. Any valid base at all of those would be equivalent to each other. Now, of course, this one with log base 3 is less than useful for us with our calculators. So if you're looking for the approximate value of log base 4 of 72, then either you can use it common log, log 72 divided by log of 4, or you can use the natural log of 72 divided by natural log of 4. Whatever the base you choose, whether it's base 10 or base e, that log of 72 over that log of 4, and that will give you the approximate value. And if you use your calculator, you should confirm and find out that both of these expressions give you the same value, which is about 3.08496. And here we want to round it to 4 decimal places. So if I were rounding it to 4 decimal places, then it would round off to 3.0850. And there we go. There's our approximate value of a log base 4 of 72. Again, for the most part, I'm not really going to be interested in finding these approximate values, except maybe in a word problem where I need to know roughly what is the answer. But for the most part, when I'm solving equations, I'm only going to want the exact value. So an answer like log base 4 of 72, even though it might look weird to you, this is totally acceptable as an exact answer.